You are listening to Talking Machines. I'm Catherine Gorman.
And I'm Ryan Adams.
And Ryan, today you're going to introduce us to Markov decision processes.
Yeah, that's right. So, we talk a lot about the relationship between machine learning and artificial intelligence. But in some ways, most of the machine learning that we do day to day feels not that much like artificial intelligence. At most, it's something like kind of pattern recognition. In particular, supervised learning is something that, seems to kind of take inputs and produce outputs. And at the end of the day, it just feels like a function that you're learning. And that is typically what you're actually doing. Unsupervised learning is a little bit more like finding structure and data and so on. And things are a little bit less well-defined. And it often feels a little bit more magical than supervised learning. But often when we really think about intelligent agents, we're thinking about, things that are making decisions, right? That perceive the world and then have to make some kind of rational plan for acting based on uncertainty that maybe their sensors receive or their perceptions. And that, and then have to make not just a decision like whether or not this is a cat or a dog, but actually really have to maybe reason with some notion of like utility over time and so on. And so this is actually a fairly big part of machine learning that doesn't necessarily always interact that much with a lot of the, with a lot of the rest of the community. So part of the reason that in some ways this kind of aspect of machine learning is underrepresented both in the way that ML is taught and also when you go to conferences like ICML and NIPS is because it's super duper hard to solve this problem. And it's really challenging to make the jump from sort of simple toy type problems to the really hard, interesting problems that we feel like get to the underpinnings of intelligence. This is part of the reason that the company DeepMind that was acquired by Google not so long ago received a lot of attention. It's because they were using reinforcement learning ideas in combination with deep learning to solve problems that really were sort of decision making over time. In this case, playing Atari games, which sounds kind of cute and trivial, but it's really hard. It's hard for humans. And so by making progress on that, they impressed a lot of people and made it feel like there was interesting progress being made in this. So I thought today we would talk a little bit about a particular formalism, and I think kind of the dominating formalism for this, which is the idea of a Markov decision process, or MDP. Now, the idea with a Markov decision process is that we're going to, like a lot of formalisms, what we're going to do is kind of imagine some fairly specific structure in the world, and then we're going to define our problem kind of very clearly. And hopefully, by being very clear about what our assumptions are and what our definition is, then we can wind up with an optimization problem or something that we can really solve. The idea with an MDP is that we have a set of discrete states in the world, and there are actions that you can take when you interact with those states. And that taking an action in a particular state causes you to move to a new state with some probability. So there's a distribution over where you might land after you take a particular action in a particular state. And this is why it has the name Markov decision process, because it's a Markovian process. So where you go only depends on your current state and the current action. And it's a decision process. You get to decide what action you're going to take. So the question is, how do we decide what actions to take when? And so kind of what makes this problem interesting is that every, say, state action pair, and you might even just think of it, every state has a reward associated with it. So when you enter some state that's good, then it maybe has a positive reward, and when it's bad, it has some negative reward. And the idea is now you're going to try to figure out how to operate in this environment in such a way to maximize how much reward you tend to accumulate over time. There are different ways we can think about it. Maybe you might ask the question, how do I accumulate the maximum amount of reward over the next 100 time steps over some finite horizon? And then there's other ideas like I'm going to live forever, but how do I accumulate maximum reward on average per time step? And then there's other ideas like I expect to live sort of forever, but I'm going to discount future rewards. And this actually sort of corresponds to interesting other kinds of utility ideas like net present value and interest rates and things like that. So getting some reward tomorrow is not quite as good as getting reward today. Mm-hmm. And so we can formalize what it is we're trying to achieve in terms of reward over time. And then our goal is to find a policy that maximizes that sort of measure of expected utility. A policy here is kind of like a really interesting thing because policy in its typical meaning in the world is something that, it's a politics thing, that is the construction of policies that are sets of rules that govern the way that an organization acts, right? That somehow create like coherence for a government or a university or something, where, when you encounter this situation, this is what you do as an institution. And policies in Markov decision processes are exactly the same. They are, when you're in this state, you take this action. But of course, there are many actions you might take in a given state. And so there are many possible policies. The question is, what is the policy that maximizes our, the reward over our expected lifetime, or sort of our expected reward over our lifetime, or whatever we have decided is going to be the kind of the game we're playing here. And so this is a very nice thing. It feels very, very narrow in some ways because we're talking about discrete states and discrete actions. But the problem is already interesting and hard, even in that limited setting. There are a variety of algorithms out there. Two of the most popular ones are things called policy iteration and value iteration. And these are kind of like dynamic programming type procedures for identifying the what a good policy is. And then there's other ideas where people solve Markov decision processes by imagining them as a kind of a game against the environment, where you take a move in this game by taking an action in a particular state, and then the environment makes a move against you by transitioning you randomly to some state. And so the environment isn't antagonistic, but it moves you randomly. Procedures like the expect to max search algorithm, for example. So ideas from game playing kind of theory come out in solving Markov decision processes. So Markov decision processes, are in some sense kind of a solved problem. I mean, that's not entirely true because there are scalability issues when the state space becomes very large or the action space becomes very, very large and continuous. But if we're talking about kind of discrete situations, then we have a pretty good handle on how to solve these well. But small relaxations of the sort of MDP idea cause the problem to suddenly become much more interesting and realistic, but also suddenly very, very challenging potentially. So the area of reinforcement learning imagines that you have an MDP out in the world that you're trying to solve, states and actions and rewards and so on, but you don't know how the world works. So Markov decision process, as I've said, you know what the states are, you know what the actions are, you know what the transition probabilities and rewards are, and you're just trying to come up with a good policy. Mm-hmm. But the reinforcement learning problem, you don't know how the environment operates. So I take an action in a particular state, I don't know where I'm going to go. And I don't know what reward I'll get when I get there. And so now you have this interesting problem where you have to learn what all of those, what all those dynamics are, in addition to learning your policy. So you have to learn a policy that somehow is going to need to learn about the world and then solve it. It may not surprise you that that's a much more realistic kind of way that the world, for things like robotics and so on, where the world is kind of coherent, but you don't have any idea what its dynamics are, and you have to discover them. And there are some very successful algorithms for this, but it's still challenging because now you're in this interesting situation where you need to sometimes do things that are suboptimal or that appear to be suboptimal because you need to figure out how everything works. Then, taking a further step, in real life, you also don't typically even know what state you're in. We can imagine trying to solve a robotics problem or something where the robot's trying to navigate around. Well, it doesn't have just like ground truth on where it is. Maybe the robot is trying to go get you coffee. It gets rewarded when it brings you coffee, but it actually doesn't have some kind of oracle that tells it exactly where it is in the building, right? And so it's going to need to take some sensor measurements, maybe using a camera or some kind of rangefinder or GPS or whatever. It's gathering data about where it is in the world or in the hallway or whatever it is. Those data that it's getting are noisy. And it needs to accumulate those data over time to try to ultimately get an estimate of what state it's in. And this, as you can guess, is an even more realistic situation. Whereas in the Markov decision process, we imagine you know exactly what state you're in and there's no uncertainty. Here, you're getting just noisy measurements of it. And this we call a partially observable Markov decision process. And so super realistic, it's exactly the kind of thing that we often find ourselves in. And suddenly the problem goes from being kind of reasonably well solved in the MDP to being almost totally impossible in the partially observable Markov decision process case. And this is because now you need to be able to reason not just about actions in the world and what their effect is on your state and reward, but you also need to reason about the information that you gather. So you actually need to include kind of a model for your own head in this action space. So some actions you might take would be bad ideas, it would be suboptimal if you knew what state you're in, but are optimal because you gather information under the partially observable case, because you gather information when you do it. And so it's simultaneously very interesting and very challenging. Suddenly now gathering information about the way the world works can have an explicit value, in particular in the kind of what are called belief state methods for solving these partially observable Markov decision processes. They're called belief state methods because unlike just the state you would have in an MDP, now you have states of your own beliefs about the world. And you're manipulating your own beliefs as you wander around and take actions, which sounds crazy, but it's kind of, there's a sense in which that's the right way to solve these problems formally. So as I said, the kind of the planning setup is kind of straightforward to write down, and there's some nice algorithms for solving it. But the second you kind of try to take that and modify it to reflect the actual uncertainties associated with the world, suddenly the problem becomes super, super hard and super interesting. But this is also why it's very difficult to make progress, and why you're not interacting with interesting planning robots all the time.
It's hard to do things in the real world. As
it turns out, realistic assumptions are challenging. I mean, this is also kind of why we often like things like kind of supervised learning, where the problem is pretty straightforward. Is this a cat or is this a dog? And that's a hard problem, but it's very well defined. And if you want to get good at that problem, you can collect a bunch of data about cats and dogs. Whereas if you want to get good at the problem of interacting with a rich and complex world, then you need to build something that interacts with a rich and complex world. And robotics is super hard. It's very hard to come up with interesting problems like this that don't require you to solve a bunch of mechanical engineering problems first. And I feel like there's been many, many people who really wanted to make progress on AI who sort of impaled themselves on robotics.
On the real world problem.
Yeah. Mechanical engineering is harder than we give it credit for.
So we'll have some papers on this on our website, thetalkingmachines.com.